Yes. Oh, now it's on. All right. So my name is Connor Bice. I'm a student at the University of Colorado Boulder. And today I'll be speaking to you about some simulations I did exploring the role of a Tachocline in M-dwarfs. So I think I can safely skip over motivating why we care about the magnetism of M-dwarfs and just get into a particular feature of their magnetism that is of interest to me. So in general, we know that the magnetism of cool stars is closely tied to the rotation rate, and particularly with M-dwarfs, they're very dominantly in the quickly rotating regime. But it turns out that the rotation rate is not the only thing that matters when examining the magnetism of these stars. So this was a figure published by West in 2008. He's since added to it, but this part is the part that I'm interested in. So we can see that there is a division among the middle spectral types, where the early M-dwarfs are dominantly inactive, while for later M-dwarfs we see a whole lot of magnetism. And we have to keep in mind that what we're seeing here does not include their histories. So the most likely explanation is that for some reason the early M-dwarfs are spinning down more quickly, and thus when we look out we see fewer of them active. However, there's also just the potential obvious explanation that maybe early M-dwarfs are just bad at magnetism. And it's probably the first one, but we're scientists and we're better than probably. So the simulations I'll be showing you guys today are hoping to rule out that second explanation. Regardless of which explanation is correct, there is a difference between these stars, and when we turn our eyes to stellar modeling, we can see one possible explanation for that, and that is at M3.5, which is coincidentally also 3.5 solar masses, these stars become fully convective. So saying that they're fully convective means that there's no radiative zone, and as we saw with the sun, the transition region between the radiative zone and the convection zone is thought to be very important. It's called the Tachocline. It has a whole lot of shear, which is useful for organizing these fields. Although, as Matt Browning pointed out, we don't actually need Tachocline in order to generate the fields, or generate fields in the sun if we're rotating quickly enough. So to say a few words about how I set my simulations up, I used a code called Rayleigh, which was being developed at CU by Nick Featherstone. It's an inelastic MHD code, fully 3D, global. It's pseudospectral, which I'll spare you the explanation of. And the background states that I'm using for these simulations come from MESA. They're 0.4 solar masses rotating at twice the solar rate. And the only difference between the two simulations I'll be showing you is that in the second one, in the first one, I cut the simulation off at the bottom of the convection zone, and in the second, I included about 7% of the radius of the star worth of radiative zone below it. And these simulations were done on Pleiades. Thank you, NASA. So this is for the first simulation that has no Tachocline. We can see on the left, longitudinally and time averaged, the toroidal field. We form two very strong wreaths of opposite polarity in opposite hemispheres, reaching within the wreaths mean field strengths of about 10 kilogauss. And when we take a cut straight through that wreath, we can see peak field strengths that are on the order of 20 kilogauss. Now, there's no Tachocline here, so this is an alpha squared dynamo. It's all being generated through helical convection. And as we have seen with other simulations, the strong fields here are quenching the differential rotation down to only about 3 or 4% of the actual rotation rate. Now, when we include a Tachocline in this simulation, we see a secondary site appear at the base of the convection zone. And all of the magnetism within the convection zone itself is largely the same. However, with this secondary site, we have an alpha omega dynamo appearing. Now, there's no real turbulence to speak of down here. It's within the stable layer. So we're just getting magnetic field deposited by overshooting convection and sheared and amplified by the layer that is present, even though the convection zone itself has very little differential rotation left. So keep in mind that the figure on the right is down within the lower wreath, and within the bulk convection zone, it's very much the same. So another thing I examined with these simulations was the time evolution of these fields. So these are sort of butterfly diagrams. They're longitudinally averaged plots of the toroidal field versus latitude and time. And we can see that in the left column for my simulations with no tachocline, and on the right, my simulations have a tachocline. In both of them, near the surface, we have the magnetic field migrating toward the poles. And down below, we can see the difference that I pointed out earlier, where at the base of the convection zone, when there is no tachocline, that is weak fields, very choppy. But when we include a tachocline, they become strongly organized and stronger by about a factor of 5. But the most interesting row here is in the middle, of course, where the wreaths are located. And we see reversals on the simulation with no tachocline sees reversals every 100 to 200 rotations. It's not overly periodic. The length does change, as you can see in this small cutout of it. While in the simulation that contains the tachocline, we only got a total of 2 reversals over 1,000 rotations, and they came about 200 rotations apart. Now, it's important to keep in mind that those reversals came at the end of the run, so if I continue it, and I am continuing it, we may see more. But in any case, the reversal time for the simulation containing a tachocline is much longer than the reversal time without. Now, this is probably the most interesting bit for the observers in the room. This is the radial field near the surface, which is the stuff that might actually have a chance to get out. So we can see in the left a comparison side by side of my simulation that has no tachocline versus a simulation containing a tachocline. And we see that there is a very marked reduction in the dipole component of the radial field when we have a tachocline. Now, the dipole is obviously responsible for, or it's the most extensive, the best spreading part of the field. So the dipole is going to be the one most responsible for the solar winds, or most influenced in the solar winds, and any kind of spin-down simulations you might do, or predictions. So having a reduced dipole field means that these tachocline simulations would most likely spin down slower than the version with no tachocline. And that is sort of at odds with the thing that I'm trying to prove here. On a side note, we see away from the polar caps in the equatorial region that the radial field is being concentrated in the downflow lanes. You can see them peeking through as they go following the differential rotation. And in some places, it is congregating enough to fully suppress the convection there. So they might be analogous to star spots, but this is still about 3% below the surface, and there's a lot of turbulence they would have to get through if they were to emerge at all. So it's suggestive of star spots, but definitely has a long way to go before any comparison there can really be made. So in conclusion, I have sort of 3 main points to take away here. and that's that these deep convecting shells are perfectly capable of organizing a strong toroidal field without a tachocline. And if you include a tachocline, then you can add a secondary site for the field to be, or for the toroidal field to be generated, and that will extend the cycling period, but it comes at the expense of the poloidal field. So while I set out to demonstrate that the idea of maybe early M dwarfs are just bad at magnetism was wrong, it's going to need a few more simulations before I can do that, because right now it's looking like it might not be totally off base.
Thanks, Connor. Questions? Chris?
Chris Johns, Crowell Rice University. In your emergent fields that you were showing are close to emergent, near the surface, the radial part. So it's peaking at about 5,000 Gauss, but what is the surface average field you're getting there?
Right, so it depends on which part of the surface you're talking about. Near the equator, it's largely
Over the whole star.
over the whole star. I don't actually have that number for you. Sorry.
But will you get it and send an email to Chris?
Absolutely.
Other questions? Way in back. You two can fight it out.
Hi, it's a very nice talk. I'm Cecilia Garrafo from CFA, and I wanted to, it's a similar question. When you show the emergent flux and you say that the lack of Tachocline leads to a stronger dipolar field, right?
Yes.
So are
At
you
least in
talking
this
about,
simulation.
excuse me? Yeah.
At least in this, yeah.
So are you talking about the total dipolar flux, or are you talking about the fractional dipolar flux? My question mainly is the total magnetic flux of the star also stronger? And what is the fraction of the dipole?
Right. So the total magnetic energy of the star has not changed by very much when you go from the non-tachocline version of this simulation and include the tachocline in it. And it is instead just that the, as you said, the fraction that is within the dipole has changed. And instead of being about a quarter of the total magnetic energy, we're seeing a reduction down quite a bit below that. I don't have the exact number on hand, sorry. I will be happy to send it to you.
Okay, so less massive stars should spin down faster, actually.
I'm hesitant to go that far with this result. I need to do
Thank you.
more with it. But.
Yes. One more question in back.
So tachoclines are physical properties of overshooting convection, right? I mean, we either have them in the convective situation or we don't have them. So in these stars, do we expect that we do have them, or so I understand that it's a parameter study, but in terms of the actual physics that's going on in the stellar interior, to some extent there's always overshoot, but the question is there overshoot of a scale height or 10 scale heights, and over what time scale is that mixing layer happening?
Right. So I think the issue here is one second. Would you mind repeating your question for me?
Well, I'm just wondering about the physical, in the particular stars you're studying,
Yes.
do we expect that those stars to build a tachocline or not, right? Because the tachocline, independent of whether there's a magnetic field or not, there is overshooting convection is a concept, right? I mean, you don't actually have a brick wall at the bottom of the convection zone ever, but in certain structural, depending on the structure of the gas, it may act like a brick wall because the penetration depth is tiny compared to any other appropriately physical units. But I'm just trying to get a sense as to, do we actually expect there to be overshooting in the bottom of these types of stars?
Okay. Using my the background that I generated from MESA, I do actually see overshoot of about half a scale, or half of a density scale height into the stable layer.
Okay, why don't we stop there and thank Connor again. Next